from the real basics right up to, well, stuff that sounds like science fiction almost.
It really covers the whole spectrum, doesn't it? From how a basic cell works to the absolute cutting edge.
So our mission, as always, is to pull out the really important bits, give everyone a clear picture of how they work, where we are now, and what's coming down the pike.
Without getting totally bogged down, right?
Exactly. Let's break it down.
Okay, let's dive in. So the core of a solar panel, it's the solar cells. Yeah.
That's the heart of it, yes.
Yeah.
A panel is basically just a bunch of these cells linked together, and the real action happens inside those cells. They're mostly made of silicon.
Silicon. Right. That's a semiconductor. We hear that term all the time.
Precisely. It's a material that can sort of act as an insulator sometimes and a conductor other times. That property is key for solar. So it lets you control the electricity flow, basically.
In a way, yes. When light hits it, it allows electrons to move. And that brings us to the main process, the photovoltaic effect.
Photovoltaic effect. Okay, sounds important. What's happening there step by step?
Okay, so imagine sunlight as like little packets of energy, photons.
Got it. Photons.
When these photons hit the silicon, they transfer their energy to the electrons in the silicon atoms.
So they kind of like knock the electrons, give them a boost.
Exactly, a boost of energy, enough energy to actually break free from the atom.
And once they're free, they start moving.
That's right, they flow. And a flow of electrons is, well, an electric current. Specifically, it's direct current, or DC.
Ah, okay. So sunlight knocks electrons loose in the silicon, they flow, and boom, DC electricity. Simple as that.
That's the fundamental idea, yeah. A direct conversion of light energy to electrical energy.
That's actually pretty elegant when you put it like that. But, okay, a panel isn't just silicon. It looks more complex, layers and things.
Oh, absolutely. It's a carefully constructed sandwich, really, designed to protect those cells and get as much light in as possible.
Okay, break down the sandwich for us. What are the layers?
Right. On top, you've usually got glass for protection, you know.
Yeah.
Weather impacts.
Makes sense. Keep the important bits safe.
Underneath that, there's an anti-reflective coating. Really important.
Because you don't want the sunlight just bouncing off the surface.
Exactly. You want it in the silicon. This coating maximizes absorption. Then you have encapsulation layers basically sealing everything up, protecting from moisture, making it stable.
Okay.
Then, the stars of the show, the silicon solar cells themselves, where the electricity gets made.
Right.
And finally, underneath or embedded, you have conductive metal plates and wires, like tiny highways to collect all that electricity and channel it out.
So the panel makes DC electricity, but my house, the grid, that's all AC, alternating current. Something needs to switch it over.
Correct. That's the job of the inverter.
Yeah.
Super important piece of kit.
The inverter. Okay.
It takes that DC output from the panels and converts it into AC electricity, the kind your appliances and everything else use, like a translator, you know, DC language to AC language.
Translator. I like that. So once it's AC, where does the power go?
Well, a few places. You can use it straight away, lights, TV, charge your phone, whatever's running.
Okay.
If you're making more power than you're using right then, the excess can go into a battery system if you have one. Store it for later, like at night.
Battery storage. Makes sense.
And often you can also send that extra power back to the main grid. It's called net metering in many places. Your meter basically runs backwards and you can get credits on your bill.
Ah, so you can actually sell power back. That's pretty neat.
It's a great incentive, yeah. Helps balance the grid too.
Okay. Seems like a well thought out system. But obviously performance isn't always the same. What makes one panel work better than another, or work better on Tuesday than Wednesday? What affects the efficiency?
Good question. Several key things. Number one is sunlight intensity. Obvious, maybe, but crucial. More sun, more photons hitting the panel, more power. Simple as that.
Brighter sun equals more juice.
Got it. Then there's the angle and orientation. You want the panels facing the sun as directly as possible for as long as possible, just like positioning a plant for sunlight.
Right. Got to catch those rays. So tilting them matters.
Big time. And tracking systems can even follow the sun, but that adds complexity and cost. Then temperature. This surprises some people.
How so?
Well, solar panels actually work less efficiently when they get too hot. There's an optimal temperature range. Excessive heat reduces output.
Huh. I would have thought hotter is always better with sun power.
Nope. A bit counterintuitive, but heat increases resistance and affects the semiconductor properties negatively. And finally, simple stuff. Dust and dirt.
Ah, yeah, if they're covered in grime, less light gets through.
Exactly. So keeping them reasonably clean helps maintain performance. Regular cleaning can make a difference, especially in dusty areas.
Okay, so sun intensity, angle, temperature, and cleanliness. Makes sense. Now, the sources mentioned different types of panels, monocrystalline, polycrystalline. What's the difference there?
Yeah, those are the main silicon-based ones. Monocrystalline, people often call them mono. They're made from a single, pure silicon crystal.
Okay, pure. Does that make them better?
Generally, yes. They have the highest efficiency because the electrons can move more freely in that uniform structure. They also tend to last longest, but they're usually the most expensive.
Right, premium option. What about polycrystalline for poly?
Poly panels are made from multiple silicon fragments melted together, so the crystal structure isn't uniform. This makes them slightly less efficient than mono.
But cheaper.
But cheaper, exactly. They offer a good balance of performance and cost, which is why they're very widely used. You see them everywhere.
Okay. And the third type, thin film.
Thin film is different. It involves depositing super thin layers of photovoltaic material onto a backing, like glass or even flexible plastic.
Flexible. That sounds useful.
It can be. They're lightweight, flexible, good for, say, integrating into building materials or for portable applications. But the trade-off is generally lower efficiency compared to crystalline silicon.
So mono for top performance, poly for cost effectiveness, thin film for flexibility or specific uses.
Got it. That's a good summary, yeah. Choosing depends on your budget, space, and efficiency needs.
Beyond the tech specs, though, there's the bigger picture, the environmental angle. That's a huge reason people go solar, right?
Oh, absolutely. It's fundamental. Solar panels generate electricity directly from sunlight, a completely clean, renewable resource. No burning fossil fuels.
So less reliance on coal, gas.
Exactly, which means significantly lower carbon emissions. It's a direct way to combat climate change and improve air quality. A major benefit.
Clean energy, can't argue with that. Okay, let's shift gears back to the nitty-gritty physics. The sources started talking about p-n junctions. Sounds complex.
It gets a bit more involved here, yeah, but it's crucial to how the cell directs the electron flow. It involves doping the silicon.
Doping, like in sports.
Huh? Not quite. It means intentionally adding tiny amounts of other elements to the silicon to change its electrical properties.
Okay, how does that work?
You create two types of silicon. N-type silicon is doped with something like phosphorus, which has extra electrons. So N for negative charge carriers, electrons.
Extra electrons, got it.
Then you have P-type silicon, doped with boron, for instance. Boron has fewer electrons, which creates holes. Think of them as spaces waiting for an electron. P for positive charge carriers these holes.
So one side has spare electrons, the other has spare spots for electrons. What happens when they meet?
You put them together, and right at the junction, electrons from the N side naturally jump over to fill the holes on the P side.
Okay.
This movement creates a depletion zone and, importantly, an internal electric field across that junction, like a small built-in slope or barrier.
A slope. How does that help?
Now, when sunlight comes in and frees an electron near that junction, this built-in field pushes the electron towards the N side and the corresponding hole towards the P side. It separates them and forces them to travel through the external circuit.
Ah, so the junction acts like a gatekeeper, directing the traffic, making sure the electrons flow out as current, not just randomly.
Exactly. It provides the necessary directionality for the current. Without the p-n junction, the freed electrons would just recombine with holes locally, and you wouldn't get much useful electricity out.
Okay, that makes sense. It's the structure that enables the flow. Now, what about that band gap energy you mentioned, around 1.1 eV for silicon?
Right. The band gap is sort of the minimum energy a photon needs to have to be able to free an electron in that specific material.
So photons with less energy just pass through or become heat.
Pretty much. And photons with more energy than the band gap still only free one electron. The extra energy is mostly lost as heat. This is a key limitation of single junction cells. Ah, okay. That leads nicely into these other materials mentioned, like perovskates and quantum dots. Are they trying to overcome those silicon limitations?
That's exactly the goal. Perovskates are getting a lot of attention. They've shown incredibly rapid improvements in efficiency in labs.
Better efficiency. How?
They have potentially better electronic properties, and importantly, their band gap can be tuned. You can adjust their composition to make them better at absorbing specific parts of the solar spectrum. Plus, they might be much cheaper to manufacture.
Cheaper and tunable. Sounds promising. What about multi-junction cells?
Multi-junction takes a different approach. It's like stacking different solar cells on top of each other. Each layer is made of a different material, tuned to capture a different slice of the sunlight spectrum. Different colors, basically.
So one layer gets the blues, another gets the reds, another gets infrared.
Something like that, yeah. By using multiple layers, you can capture energy from a much broader range of photon energies, overcoming that single band gap limitation of silicon and significantly boosting overall efficiency. Clever. And quantum dots, they sound very sci-fi.
They are pretty amazing. These are tiny semiconductor nanocrystals just a few nanometers across. The cool thing is, their band gap, the light color they absorb best, can be precisely controlled just by changing their size.
By size, really?
Yeah. Smaller dots absorb higher energy light, blues. Larger dots absorb lower energy light, reds. So you can engineer them to perfectly match the solar spectrum. Plus, there's theoretical potential for things like multiple excitant generation.
Multiple excitants, you mean one photon creating more than one electron-hole pair?
Exactly.
Yeah.
If that could be harnessed efficiently, it could dramatically increase cell efficiency beyond current theoretical limits. It's a huge area of research.
Wow, okay. So lots of routes to higher efficiency. Now, let's talk about getting the most power out moment to moment. Maximum power point tracking, MPPT.
Right. MPPT is crucial, especially in real-world conditions. See, the exact voltage and current at which a panel produces its absolute maximum power changes constantly.
Why does it change?
Because of changing sunlight intensity, clouds moving over, sun angle changing, and changing panel temperature. The sweet spot for maximum power output is always shifting.
Okay.
MPPT is essentially a smart electronic system, usually built into the inverter or a charge controller, that continuously monitors the panel's output and adjusts the electrical load, the voltage and current draw to stay right at that peak power point.
So it's constantly fine-tuning to squeeze out every last watt, no matter if it's sunny or partly cloudy.
That's the idea. It dynamically optimizes the energy harvest in real time. Without MPPT, you'd lose a significant chunk of potential power, maybe 10–30%, depending on conditions.
Makes a huge difference then. Now, despite all this optimization, some energy still gets lost, right? The sources
Yeah.
mentioned loss mechanisms.
Absolutely. No energy conversion process is 100% efficient. There are several key ways energy is lost in a solar cell.
What are the main culprits?
One big one is recombination loss. That's when a freed electron basically finds a hole and they recombine, releasing energy as heat or light before the electron contributes to the current.
So they cancel each other out too soon.
Exactly. Then there's thermalization loss. Remember how photons with energy way above the band gap still only free one electron? All that extra energy just turns into heat within the silicon? Wasted energy.
Okay, heat loss. What else?
Reflection loss, light bouncing off the surface instead of going in. We talked about anti-reflective coatings to minimize this. And resistance loss, just the inherent electrical resistance of the materials, the wires, the contacts, like friction for electrons.
So recombination, thermalization, reflection, resistance, lots of things trying to steal the energy.
And researchers are constantly battling all of them, trying to improve materials, cell designs, and coatings to reduce these losses.
Which brings us back to those advanced anti-reflective coatings. You mentioned moth eyes.
Yeah, it's a great example of biomimicry. Moth eyes have evolved these incredible nanostructured surfaces that are extremely good at absorbing light and reducing reflection, even at wide angles. So scientists are creating similar nanostructures on solar cells.
Mimicking nature. Cool.
Other advanced coatings use multiple thin layers of dielectric materials. By carefully controlling the thickness and refractive index of each layer, you can create optical interference effects that cancel out reflections across a wide range of wavelength.
Very clever optical engineering. What about bifacial panels? You touched on those capturing light from both sides.
Right. Bifacial panels are designed to be active on both the front and the back.
How does the back capture light?
From reflected light. Sunlight that hits the ground or surface behind the panel and bounces back up. Think snow, light-colored roofs, or specially prepared reflective ground coverings.
Ah, so you capture the bounce back light too.
Exactly. Depending on how reflective that rear surface is, the albedo, and how the panels are mounted, you can get a significant power boost. Sometimes 10%, 20%, even up to 30% more energy compared to a standard one-sided panel in the same spot.
That's a nice bonus without needing more roof space.
Smart. And AI and IoT are getting involved too. How are they helping?
They're starting to play a big role in optimization and management. AI can be used for predictive maintenance.
How? By analyzing sensor data from panels, temperature, output, maybe even acoustic signals, AI algorithms can predict potential failures or degradation before they happen. Allows for proactive repairs.
Catching problems early.
Good. AI also improves smart tracking systems. Instead of just following a pre-programmed path, AI can use real-time weather forecasts, cloud cover data, and learning algorithms to position the panels even more precisely for maximum energy capture throughout the day.
So predicting the best angle even with changing clouds.
Exactly. And on a grid level, AI helps forecast solar energy production much more accurately, which is crucial for grid stability. There's even exploration of using blockchain for decentralized energy trading between people with solar panels, peer-to-peer energy markets.
Wow, okay. AI touching everything from maintenance to grid integration to maybe even buying and selling power directly. The systems are getting really intelligent.
They really are. It's moving beyond just panels and inverters to a whole smart energy ecosystem.
All right, let's push further into the really advanced stuff. The sources mentioned quantum mechanics playing a role. Excitons, tunneling. This sounds deep.
It definitely goes deeper into the fundamental physics. We mentioned excitons briefly, that bound electron-hole pair created when a photon is absorbed. Getting them separated efficiently to create current is key.
And quantum mechanics helps understand that separation.
It governs it entirely. Researchers are looking at leveraging quantum effects like quantum coherence, where particles can exist in multiple states at once to potentially improve how charges move through the material with fewer losses. It's complex, still theoretical in many ways for practical cells.
Okay, coherence. What about hot carriers?
Right. Remember thermalization loss, where extra photon energy becomes heat? Hot carriers are those electrons initially excited to very high energy levels before they cool down and lose that extra energy.
So the idea is to grab them while they're still hot.
Exactly. If you could extract those hot carriers and use their extra energy before it turns into heat, you could significantly boost efficiency. Materials like perovskites and some quantum dot structures show potential for doing this, but it's technically very challenging.
Harvesting the heat energy, basically. And surface plasmon resonance.
That involves using tiny metal nanoparticles on or near the solar cell surface. Light hitting these nanoparticles can excite collective oscillations of electrons, plasmons, which can then concentrate the light very effectively into the nearby semiconductor material, enhancing absorption.
Using metal bits to funnel light better.
Okay.
It's clear that understanding quantum effects is becoming really important for the next generation of solar.
Absolutely. Pushing efficiencies higher requires manipulating things at that fundamental quantum level.
And it seems that multi-junction cells are the main way we're currently pushing past the basic silicon limits, right?
Yeah.
You mentioned the Shockley-Queisser limit for silicon.
Yes, that theoretical cap of around 33% for a single p-n junction cell. Multi-junction cells are the proven way to beat that. By stacking layers of different materials like gallium arsenide, GAAs.
Used in space, you said?
Yep, GAAs is great for space because it's highly efficient and radiation resistant. You can add layers of indium, gallium phosphide, germanium, other 3V materials, each layer optimized for a different part of the solar spectrum.
Capturing more colors?
Capturing more colors and using the energy of each photon more effectively. State-of-the-art 4-junction cells, especially when used with lenses or mirrors to concentrate sunlight onto them.
Concentrated solar power? CSP.
Right. Under concentration, these multi-junction cells have hit over 50% efficiency in labs. It's incredible, but also very expensive, so mostly used in niche applications like space or utility-scale CSP, not typically on rooftops.
50%. That's a massive jump.
Yeah.
And the sources talked about even more advanced light management, photonic crystals, metasurface.
Yeah, this is about controlling light pathways within the cell at the nanoscale. Photonic crystals have repeating structures, kind of like a crystal lattice for atoms, but this one interacts with photons. They can be designed to trap specific wavelengths of light, forcing them to bounce around inside the active layer longer, increasing the chance they get absorbed.
Trapping light.
Okay.
What are metasurfaces?
Metasurfaces are even more exotic. They're ultra-thin, engineered surfaces with sub-wavelength pattern structures smaller than the wavelength of light itself. They can manipulate light in really unusual ways, bend it sharply, focus it, change its polarization, all in a very thin layer. Potentially better than conventional optics for things like trapping light or steering it.
Wow. And Jurian optics, gradient refractive index.
Jurian optics use materials where the refractive index, how much the material bends light, changes gradually across the material. This allows for sophisticated light bending and scattering within the cell to, again, enhance absorption and minimize reflection. And quantum dots can be integrated with these structures, too, for fine-tuning absorption.
It's like creating tiny internal optical obstacle courses for the light to make sure it gets absorbed.
That's a pretty good analogy, yeah. It's all about maximizing the interaction between photons and the photovoltaic material.
And AI is getting even more involved here. Self-healing cells.
The potential is there. AI-enhanced MPPT is becoming more predictive, as we discussed, but research is looking into, yes, self-healing materials. Imagine incorporating microcapsules of a healing agent into the solar cell layers. If a microcrack forms, it breaks the capsules, releasing the agent to fill the crack. AI could potentially monitor the cell's health at a microscopic level and even trigger or guide this process.
That sounds like science fiction. Repairing themselves.
It's definitely futuristic research, but the idea is to dramatically extend panel lifespan and maintain peak performance for decades. And AI is also crucial for designing these complex materials and structures in the first place, simulating how they'll interact with light.
Okay, the future is smart and self-repairing, maybe. Let's talk deployment again. Floating solar, FPVs.
Floating photovoltaics, yeah, putting solar farms on bodies of water like reservoirs, lakes, even potentially offshore.
What's the advantage there?
Several things. One, it saves valuable land space, which is a big issue in densely populated areas. Two, the water has a cooling effect on the panels, which, as we know, can actually boost their efficiency slightly.
Natural cooling.
Plus, covering the water surface reduces evaporation, which can be a significant benefit for water reservoirs in arid regions, and it can also limit algae growth. So, multiple potential benefits.
Interesting synergy there. Okay, now for the really big vision. Space-based solar power. Beaming energy down.
It's the ultimate ambition for some. The idea is huge solar collector satellites in geostationary orbit where they get uninterrupted sunlight 24/7.
No nighttime, no clouds.
Exactly. They collect massive amounts of energy, convert it to microwaves or maybe lasers, and beam it down to large receiving antennas, rectennas on Earth.
Beam energy wirelessly. Is that even possible on that scale?
The physics works. Microwave power transmission has been demonstrated. The challenges are enormous, of course, the cost of launching and assembling these massive structures in space, the efficiency of the beaming and conversion process, atmospheric effects, safety.
Huge engineering hurdles.
Absolutely massive.
Yeah.
But the potential payoff, constant, clean, baseload power from space, is why it remains a long-term research goal for several countries and private companies.
A truly global power source, potentially. And back on Earth, the hunt for new materials continues beyond silicon and perovskites. Carbon nanotubes, graphene.
Yes, the search is always on. Perovskites are still leading the charge for near-term breakthroughs due to rapid efficiency gains and potential low cost, with efficiencies over 30% reported now.
Over 30%, wow.
Carbon nanotube-based cells are attractive because they could be incredibly lightweight and flexible. Imagine solar cells you could literally roll up or integrate into fabric. Still early days for efficiency, though.
And graphene, the wonder material.
Graphene is being explored mainly as a transparent conductive layer or to enhance charge extraction due to its amazing electrical conductivity, maybe improving performance or enabling new types of cell architectures. Lots of research, but scaling up remains a challenge for many of these newer materials.
It feels like a race on multiple fronts, improving silicon, perfecting perovskites, exploring totally new options.
It really is. There's no single magic bullet yet, more like a whole portfolio of advancing technologies.
Okay, I thought we were at the edge, but the sources went even further. Quantum electrodynamics, QED, entangled photons.
Right. This is diving into the most fundamental theory of light-matter interaction we have. QED describes things like the wave-particle duality of photons, exactly how they are absorbed, reflected, transmitted at the quantum level.
So it's the rule book for everything we've been talking about.
Pretty much, yeah. Understanding QED deeply could, theoretically, reveal new ways to manipulate these interactions. Concepts like using quantum coherence effects more effectively, or even harnessing quantum entanglement.
Entanglement.
Yeah.
Like the spooky action at a distance. How would that help solar?
It's highly speculative, but the idea might be something like using entangled photon pairs to somehow enhance absorption or reduce losses. It's really fundamental physics research at this stage, not something you'll see in a panel soon, but it pushes the boundaries of what might one day be possible.
Mind-bending stuff. And photonic bandgap engineering and hyperbolic metamaterials, more advanced light control.
Even more advanced, yes. Photonic bandgap engineering is about creating materials that literally forbid light of certain frequencies from traveling in certain directions, like an insulator for light. This could be used for perfect reflection or trapping. Hyperbolic metamaterials have even weirder optical properties, allowing light to propagate in ways not possible in normal materials. The hope is that these could lead to breakthroughs like a highly efficient multiple excitant generation.
Designing materials with truly alien optical properties. Incredible. And the multi-junction cells just keep getting more complex. 4 junctions, perovskite silicon hybrids.
They do. The state-of-the-art involves stacking 4 or even more junctions of 30 materials for those record efficiencies, especially under concentration. A really active area is creating tandem cells, stacking a perovskite cell on top of a standard silicon cell.
Why that combination?
Because perovskite is good at absorbing the higher energy blue and green light, while silicon is better with lower energy red and infrared. The perovskite top cell captures the high-energy photons efficiently and lets the rest pass through to the silicon bottom cell. It combines the potential low cost of perovskites with the proven stability and infrastructure of silicon. A best of both worlds approach.
That sounds very practical, combining strengths.
And there's even research into all-carbon solar cells, trying to move away from silicon and potentially rare metals altogether, using things like nanotubes and fullerenes. Still very much lab work, but aiming for sustainability and low cost.
The materials science is just relentless. And AI, again, neuromorphic AI, what's that?
Neuromorphic computing tries to build computer chips that mimic the structure and function of the human brain, with artificial neurons and synapses. The idea for solar is to use this brain-inspired AI for incredibly adaptive and efficient real-time energy management, maybe even controlling energy flow at the nanoscale within devices, or optimizing vast grids in ways current AI struggles with. Also using AI for detecting tiny defects during manufacturing.
AI that thinks more like a brain to manage power. Okay. And we're still talking seriously about orbital and even lunar power stations.
The visions are definitely still alive and getting more serious study, especially as launch costs come down. Gigawatt or even terawatt scale power satellites beaming energy down remain a long-term goal. And yes, proposals exist for building solar farms on the moon, maybe using lunar soil regolith, which contains silicon and metals, as raw material.
Building solar panels on the moon from moon dust.
That's the ultimate ISRU in situ resource utilization dream for lunar colonization and power. Extremely challenging, obviously, but conceptually possible. Lightweight tech like quantum dot arrays would be key for space deployment.
The scale is just hard to comprehend. And back on Earth, combining solar with other energy harvesting, solar thermal hybrids.
Yes, trying to capture not just the light energy, but also the waste heat. Thermoelectric generator, TEGs, can convert a temperature difference directly into electricity. So attaching TEGs to the back of hot solar panels could generate a bit of extra power from the heat.
Using the waste heat instead of just letting it reduce efficiency.
Exactly. Or using advanced cooling systems with special nanofluids that not only cool the panels effectively, but also transport that captured heat somewhere it can be used, maybe for water heating. Phase change materials could also store heat collected during the day for later use, maximizing total energy capture.
Squeezing every bit of energy out and right down to the smallest scale, quantum dots and 3D nanostructures. It's getting incredibly precise.
Extremely. Techniques like atomic layer deposition allow building up materials literally one atomic layer at a time, creating perfectly smooth interfaces to reduce electron scattering and losses. Researchers are exploring 3D printing of quantum dot structures to create complex architectures optimized for light absorption across the full spectrum, even techniques to manipulate how long photons stay inside these structures to boost absorption, nanoscale engineering at its finest.
Controlling matter atom by atom for better solar cells.
Yep.
Okay. And finally, the grid itself, hyper-intelligent grids, blockchain. What's the ultimate vision here?
The vision is moving away from a centralized grid with passive consumers to a much more dynamic, decentralized, and intelligent network. Hyper-intelligent grids would use pervasive sensors, AI forecasting, and automated controls to instantly balance supply and demand from millions of distributed sources, rooftop solar, batteries, EVs, etc., ensuring stability and efficiency.
A self-managing grid.
Largely, yes. And blockchain could provide a secure, transparent platform for tracking energy generation and enabling direct peer-to-peer trading of energy, cutting out intermediaries and creating more localized energy markets. A truly democratized energy system.
It paints a picture of a really transformed energy landscape. Cleaner, smarter, more distributed, more resilient.
That's the goal, driven in large part by the ongoing revolution in solar technology and related fields like AI and energy storage.
Well, this has been quite the journey, from basic silicon to quantum coherence, and lunar power stations. Hopefully, this deep dive has given everyone a much clearer and maybe more exciting picture of solar tech than just panels on a roof.
I certainly hope so. It's fascinating to see how it spans basic physics all the way to these incredibly ambitious future concepts. The pace of innovation is just remarkable.
It really is. So, considering everything we've touched on, advanced materials, AI, quantum effects, space-based ambitions, what do you think might be the single biggest breakthrough that really shifts the needle, that truly revolutionizes how we power the world with the sun? Definitely something to ponder.
It's tough to pick just one, isn't it? So many promising avenues converging. The synergy between materials science and AI seems particularly potent right now.
Indeed. And really, we've only scratched the surface here. If any specific part of this, quantum dots, tandem cells, space power really caught your interest, there's a whole universe of research out there to explore. Thanks for taking this deep dive with us.